So we wanted to broaden the subjects that was already that was supposed to be plagiocephaly orthopedics to 3D printing from concepts to final products, because we want to give a better overview of why 3D printing is such a good technology, especially for health. So to do that, we have 3 parts. The first part would be to discuss in introduction the technology in itself, what's the difference between additive manufacturing and subtractive manufacturing, and why is it so well adapted to health. The second part will be about design for additive manufacturing, because when someone is using 3D printing or additive manufacturing, they have to keep in mind that the way you design a part for traditional manufacturing is absolutely not the same as the way you would design a part for 3D printing. The second part would be about biomedical application of additive manufacturing. So there we will try to show you a few examples of what is possible to do with additive manufacturing. And on the last part, Madi will talk to you about post-processing on additive manufactured parts, because that is a really important subject. Most of the parts that are done with 3D printers, they are actually not finished when you take them out of the printer. So the first part is to show you what's the difference. Oh no, you wanted to do this one.
So I think it was well introduced. There is some difference between additive manufacturing and subtractive manufacturing. For the first part, we start with a bulk of material, and we remove away a lot of things. For the second one, we start to build our part layer by layer. However, there is a lot of things to increase. We must take a look in the surface, because we have a rough surface, and also there is some limitation as presented before. For example, we have a freedom of the design, but we have some supports, and it will be interesting to take a look of this for the conception and also for the production.
To illustrate the difference between subtractive and additive manufacturing in terms of costs, a good representation is those 2 curves, and on the x-axis on both curves you have here the number of parts you want to print. So are you printing 10, 100, 1,000, a million parts? And here the level of complexity of your design. By that we mean if you're designing just a simple cube, it will be here, and if you're designing a church or something like that, you'll be on the other hand. So what's interesting is that on both graphs you have subtractive manufacturing here. In the decrease you see here is because when you are doing subtractive manufacturing, you can more easily decrease the price when you do a lot of pieces. And if you just manufacture one part, of course it would be much more expensive. But that is not the case with 3D printing. With 3D printing, you can print one part or 10,000 parts. The price will be always exactly the same. So there's one point above which 3D printing starts to be more expensive than traditional manufacturing. But under that, you're good to go. And that's one of the good points for health, because when you are manufacturing parts for health, each part is unique and each part is customized for the patient. So you are nearly always under this point. The other thing here about complexity is that, as I said, you have to customize the part to be perfectly adapted to the person. So usually the level of complexity is quite high, and because the level of complexity is quite high, the difference in costs is in favor of 3D printing. Now, to give a quick overview of additive manufacturing, because I'm not sure that it's clear for everyone, there are 7 big families of 3D printing, not 3D printing, additive manufacturing processes. The first one would be material extrusion, which is the one everybody knows. You put a wire in, you heat it up, and you create your part like that. The second one is powder bed fusion. For this one, you just apply a thin layer of powder on a table, and with a laser or with electron beam, you can melt specific parts. So those parts will be the section of your piece, and then you will put another layer, melt it again, another layer, melt it again, and at the end you have your parts. This one is the VAT photopolymerization, so you can maybe you have heard the term stereolithography, and that is when you have monomer resin and you polymerize the resin with a UV laser. Next, you have material jetting, so the aim is to jet fused material onto a table, which will cool down when it touches the material, and that way you can print the piece. Then you have binder jetting, so there again you will use layers of powder and you will basically drop glue at it to make it stick together. Then sheet lamination, you will use sheets of paper, cardboard, wood, metal, polymer, whatever you want. You cut the section you want to have, you put your sections all together, and then you get your piece. And the last one will be direct energy deposition. On this one, you will have a laser or an electron beam, and you will inject powder into that beam to print your parts. All those additive manufacturing processes is what you have here, of course, when you want to produce your parts, and above that, you will have to design your parts, and when you know that you are going to use additive manufacturing, you have to use what is called DFAM, which is designed for additive manufacturing, which is a really, really specific way to design your parts. And then after that, one of the most important parts is, of course, the post-processing, because it's always under-evaluated how important it is to post-process your parts. So now we'll talk a bit further about designs, and for that I will take the example of what Julien Gardon was working on in Troyes. So plagiocephaly is a malformation of the skull of children, and it happens quite often, and if you take care of it during the first 2 years of the child, then you can fix the problem as simple as it is to fix crooked teeth, for example, because the parts that we are going to create with additive manufacturing is basically braces, but for the skull. So what we do is that we take the children and we do a scan of his head, and with the scan of his head we are able to create a helmet that will try to help the skull form correctly. So to do that, 3 main steps. First, as I said, we scan the head, and then we'll be able to see where the deformations are. Then, with that, we will be able to design the helmet, and with simulations, we will be able to apply a specific shape to the helmet to make it able to help the kid get his skull back into the proper shape. Another way to design for additive manufacturing is, well, another thing that is allowed with additive manufacturing that is not with standard manufacturing processes is that you can embed channels inside of parts, and channels that are way longer or more complex that you could drill. Sorry. So basically, for this case, you have here it's a hip prosthesis, and the aim was to be able to inject drugs inside of the patient's bone, and to do that, this heat prosthesis has channels that were not drilled after the part was created, but integrated during the design, so that the printed part already has those channels. And because of that, we are able to make, because of 3D printing, we are able to make that, which would be completely impossible otherwise. Now I will just show a few other examples of additive manufacturing. One that is really interesting is the dental applications and the dental implants and the dental crown. What is really interesting about this is that it's one of the few things in which 3D printed is already a better, cheaper, and easier way to do things than what was done before. So what we would do is we just scan the inside of the patient's mouth and then do the model of that. And after that, we are practically able to print a tooth for temporary crown or temporary tooth, which would be very easy to print, very fast to print. And the major advantage of that is that when you do the definitive crown or the definitive tooth with a metal, you will have similar mechanical properties than normal prosthetic, normal fake tooth. And all that I said before. And the only step after the only step after the 3D printing would be to manually polish the tooth so that they won't be all rough. Yes. Okay, so just another few examples before Madi finishes up. What you can see here is what was done in China a few months ago, I think. So there was a child that has no lower jaw. I don't know if it was because of cancer or an accident, I don't remember. But they were able to 3D print in titanium this jaw. The other thing here is a small bone inside of the ear that makes you able to hear everything. So it was 3D printed in titanium as well. This one is it was done a few weeks or months ago maybe, and it's a heart that was 3D printed in the USA, where it happened a few months ago as well in Israel. And this heart is kind of functioning, not perfectly yet, but it's kind of working. And the only thing is to be able to print a bigger one, because this one is like the size of my palm. After that, we have here a rib cage in titanium, which is really interesting. Is that because we 3D printed it? I don't know if it's easy to see it here. No, not really. But the inside actually of the titanium bones are not completely filled. You have lattices inside, which makes possible to have really lightweight materials that are more resistant than bones. I will just put that now. Sorry, I'll just put this because this is a French company that 3D prints skin grafts. So what they do is that they use it's not working. So they use laser pulses to strike a film of cells. And those cells will be then projected onto your burnt skin maybe, or under a substrate on which you can 3D print the skin that you need to graft to the patient. So this is not commercially available yet, but it will be in the next few months, years. Okay, so and the last thing I wanted to show you is that we are perfectly able to 3D print teeth like these, and of course you can see the difference between the teeth that when they get out of the 3D printer and the teeth once they are polished by a smart person. And that's the parts that Madi is going to talk about.
Thank you very much. So, before to start, I would like to remember you something. Conventional or additive manufacturing parts, both of them have some limits, some advantage. And the challenge, it's the same, is to enhance the surface and also to enhance the property, mechanical property of this part. So when we start, there is different surface quality, for example, for one or the other, and we have a roughness. With additive manufacturing, the problem is the roughness of the part. Also, we have some defect or micro cracks in the surface. We can increase hardness, but we have some hardness, it's dependent of the microstructure. We have microstructure and we have a tensile residual stress. This part, it's very important. Here, with the tensile residual stress, we can affect the time life of our parts. So all of them, we can decrease, we can have some defects in the hardness or wear resistance, and also of the lifetime of the part. We can also induce a post process. With that, we can reduce roughness. We can reduce also micro crack, and the advantage here, we induce a compressive residual stress, and also we can increase hardness, and we can induce a nanostructure in the surface. I will talk a little bit about the selective laser melting. It's one of the 7 processes that's used. There is a lot of research that done about to optimize the process parameter. Here, for example, we have the laser power, we have the scan strategy, and we can play with them. For us, we choose the surface post-treatment, and we would like to reduce porosity and to induce compressive residual stress. For example, here is some example that we can use SLM part, and we use it really in the biomedical application. Here, for example, combined with additive manufacturing and optimization topology for DFM, we can customize and have some unique plan. We use a mechanical post-treatment. Here it's called SMAT, Surface Mechanical Tension Treatment. Here we can see our sample, and we use some spherical ball, and we impact our surface randomly. With this process, you can see here, we have the shot. We induce some deformation in the surface, and the material would like to become in the original state. Like this, we induce the compressive residual stress. So, in this work here, we use it in the austenitic stainless steel, and we can see here as fabricated, SMAT low, SMAT high. It's 2 different levels of SMAT. So we increase the hardness, like here, for example, SMAT low, and SMAT high, we increase it in the surface. Also, we can see the surface roughness, we reduce it, or we decrease the roughness, and we have a smooth surface. Also, we increase the tensile property of the material. However, we lose some elongation. Here we can see it also. In the as fabricated sample, we have tensile residual stress on the surface. But after the SMAT, we induce compressive residual stress. And we have some results that can show an increasement of the life cycle fatigue. So we increase the fatigue property of our material. We have done the same thing, the same thing with titanium. And for example, here you can see the roughness decrease with the time. It's the time of the SMAT treatment. On the other side, here we have done two treatments: mechanical treatment and thermomechanical treatment. And here we increase hardness in the surface. And also, we induce compressive residual stress here without heat treatment, with the heat treatment. However, you can see SMAT for austenitic stainless steel or titanium that's very used in biomedical application. We induce this compressive residual stress. Thank you very much.